because of the looks on your faces, I proved where pi r squared came from. Just to show them that these things didn't come up in a vacuum. They exist because math works. And that was directly due to the fact that when I drew this picture and was talking about looking at a small little box here, somebody in the room just made this like gaspy noise, and I was frustrated with it. But this little box, which was created by saying, okay, this distance is r, and this is dr, and this distance is, not that one, I don't want that one, I want this one. This distance is r d theta. If I take those two and I want to find the area of that little box, the area of that little box is dr, which is a length, it's in meters, times r d theta, which is also a length in meters. And then I tried to make the statement that that is not a true square. So multiplying it together won't really give you the area, it'll give you something close to the area. But the beautiful thing about calculus is that this is at such an infinitesimally small area that it is a square. I want you to imagine, on your computer monitor, it's made up of little pixels and little dots. This square right now is probably being made up from 100,000 dots. But at the at the integral level, it's 4 dots, right, that define the square, which makes it a perfect square. You think about shrinking it all the way down to super, super small, it is a square. It's so infinitesimally small, that's why you can do this. And for the people who didn't believe me, this equals dA, a piece of the area of a disk. If I integrate this around the entire disk, I should be able to get the area of a disk. That's what I did in a second. I'm going to do it here real quick because it only takes a minute. But I want to point out that to write the integral on the right side of the equation, there are 2 derivatives, dr and d theta. I can't integrate just one of them. To get the area, I have to integrate across both, which is why what I really need to do is write this as the double integral of dr times r d theta. Now, there is an important element here about doing a double integral. In real math, which you will learn someday, the order that you do this in can be important. It is plausible that one of them is related to the other, especially for things where maybe the radius changes depending on where you are on your object. Imagine an ellipse. You see how the radius of an ellipse from its center would change as you would go around the ellipse. So you might need to know how it changes. You might need a formula for an ellipse if you wanted to integrate the radius around an ellipse. So things where it's not uniform, where there's a connection between where you are in one dimension versus where you are in another, might require more complicated math. But these 2 things are independent. There's both symmetry with the radius all over, and it's a nice, convenient circle. So because of that, I can group up r and dr and leave d theta separate, and I can do this integral in 2 different ways. I can do it like from the inside out, like it's parentheses, or I can quite literally split up the parts of the integral that are continuous and do them as 2 separate integrals. Either one of these will be fine. Pick your favorite and go. Since in the other class I did this version from the inside out, in this class I'm going to do this version because it's actually easier. So I got to set my limits though to make sure I cover an entire disk. So I need to go from the center of the disk to the outer edge of the disk. And I need to go from some point on the edge of the disk all the way around 2 pi radians. I don't have to worry about any trig function here because there is no trig function. So I don't have to worry about making sure that there's no positive and negatives, anything like that. I just integrate around the circle. So the first one will be 1/2 r squared evaluated from 0 to capital R. I gotta keep putting brackets because Mr. Bright likes the brackets. Times theta evaluated from 0 to 2 pi. Good so far? Good. Nobody said a word, so it's gotta be just fine. I'll point out that the first one's going to be 1/2 capital R squared, and the second one's going to be 2 pi. Multiply all that together and you get pi r squared. But no, pi r round. No, pi r squared. It's that stupid joke. I just popped in my head. Sorry, I apologize. But I want to point out that, see, it works. Treating this piece like it is a square and multiplying it together is the way you do an integral in 2 dimensions using polar notation. Actually, what you will find in math is that rectangular integrals are dx dy, and polar integrals are r dr d theta. These are the standard integrands for rectangular shaped objects where the area is important, and for circular shaped objects where area is important. There's a similar set for 3-dimensional coordinates, a set of predefined integrals that will allow you to take areal and volumetric integrals. That is Calc 3, one of the coolest calc classes you'll have to take until you take differential equations, which is like the bomb for you guys who like math. So we're going to erase all of this because although this was tons of fun and I really enjoyed it, that's not what we were set out to do. We were set out to find the moment of inertia, and all we just did right now was find the area of a circle. But I want to know the moment of inertia of the circle. So to find the moment of inertia of the circle, I have to remember that this little tiny piece actually has mass, dm. And its mass will be equal to the density times the area. The density of the disk will be the entire mass of the disk divided by the entire area of the disk. That is the density of the disk. So my dm is going to be sigma, lowercase sigma for areal density, dA, or sigma dr r d theta. That's my dm. Moment of inertia is the integral of r squared dm. I don't have to do anything special with the r. Any point on this circle, any square I would decide to look at on this circle is a distance r away from the center. So unlike the ring, I don't have to worry about it. Now, if I was trying to look at an axis through the center like this, I would. It wouldn't be a radius away or a piece of the radius away. I'd have to do something else. But for about its center like this, spinning it like a CD, everything is based on that center. I can use a radial distance. So, substitutions, lots of them. I will have a double integral of r squared times sigma dr r d theta. Do you know how many times in my physics class when we'd have to say r dr, we would make little pirate noises? I know it sounds sick, but when you're a physics major, you're around some really, it goes beyond nerdy and geeky. I got to be honest with you. It's like a new category you didn't know existed, because it's like nerdy and geeky, but more importantly, nerdy and geeky, but revel in it. Like telling physics jokes is not just okay, but encouraged. Like you're hoping for a new one, as opposed to, oh my God, did he really just say that out loud? So once you translate from high school to college, and you're actually in college, things change dramatically. This caste system you're stuck with goes away, and you can actually be okay being smart in front of other people without having to hide it and say, yeah, I'm in smart classes, let's not talk about it. Or just dump your drink all over the ground. It's okay. No one will ever know. All right, so keeping on with our tradition here, I'm going to set up my limits of integration, 0 to r and 0 to 2 pi. I'm also going to go ahead and collect like terms, so I have r cubed sigma dr d theta. Good so far? Why aren't you good there?
I still get double integral thing.
It's okay. I don't think it's going to just spontaneously come. You're going to have to practice. But I have 2 of these, right? Because I have two of them, I have to make sure I have added up all the pieces related to r and all the pieces related to theta. So I have to make sure I go from the inside edge to the outside edge. That's r. And I have to make sure I go all the way around the disk. That's theta. I have to do it. I have to do each. It's not just going to dawn on you. Your brains don't work this way with what you've learned in other classes. It takes time. Now, I'm going to do this the same way I did it before. I'm going to pull the sigma out. Now, the integral from 0 to r of r cubed dr times the integral from 0 to 2 pi of d theta. The biggest transition is understanding that d theta is just a number and dr is just a number. And you're just adding up all the numbers related to theta and all the numbers related to r. Once you realize it's a sum and you understand that it's just a sum, it will begin to make that easier. Yes, sir?
I was confused on why it turned from a single integral to a double one when we're plugging in.
Like from here to here?
Yeah.
Because we are describing the mass in terms of two dimensions. Right? We're changing it from adding up every piece of mass, which is one dimensional, every one of these boxes. Right? We're adding all these boxes up. But to add them up, we had to write their mass in terms of where they are on the disk. So where this one is has its own r and its own theta. And where this one is has its own r and its own theta. And where this one is has its own r and its own theta. So I have to add up all the possible r's and all the possible thetas for each to describe where each box is. That's why it becomes a double integral. And if that explanation doesn't work, the other reason it becomes a double integral is because area is always the product of two dimensions. So to compute any area, I'm going to have to sum in two dimensions. You could probably imagine that if this mass was something three-dimensional, then I would have to transform this from a single integral for mass to a triple integral for volume to describe all three dimensions where a piece of mass might be located. Ultimately, remember, the big goal here, when it comes to writing this, is to find a way to describe each mass geometrically, not based on how much mass is there necessarily, but where that mass is located. Because we're trying to add up not just how much mass is in the object, but how far away that piece of mass is from the axis of rotation. Because that's the real sum here. So it's not, remember, if you look at the sum, it's a sum of mr squared. This box right here has a mass, but I'm not adding up the mass of the object. That would just be m when I'm done. I'm adding up how much mass is here and how far away is it from here. So to do that, I have found a set of coordinates I can use to describe where that mass is. My set of coordinates are r and theta. At the same time, I have to use r and theta then to define how much mass is there. So I defined the area of that little piece and multiplied by the density so that now I know how much mass is there in terms of where it is. That's what this process is about. Is that helping a little bit? Kind of. At least let me finish. So you do see there's only one more thing to do here, right? I'm right at the end. This will be sigma. R cubed will be 1/4 r to the 4th times 2 pi. Now, what's sigma? So, m over pi r squared times 1/4 r to the 4th times 2 pi. Cross out all the things that cancel, and you will get 1/2 mr squared. All right.